started talking about these, or at least we mentioned them in passing in chapter 16 mostly. 16 mostly? Honestly, both of the last two chapters. 18 and 16, I guess. 17 doesn't feel like a chapter, it was a day. We've already kind of talked about these a little bit, but now we get to do some complicated things that end up making new carbon-carbon bonds. And, I mean, we're used to making new carbon-carbon bonds. That's like half of what we do, or we're used to making new bonds, sometimes between carbon, sometimes between nitrogen or oxygen nucleophiles, but you know, this is going to end up doing some carbon-carbon bonds. So, an enolate anion is formed by treating an acetaldehyde with base. I mean, okay, enolate anions are formed by treating acetaldehyde with base, or any aldehyde, or a ketone for that matter, with base. Part of the reason that, so we're gonna start doing alpha carbon chemistry, right? We do deprotonate, I don't know, call it water, deprotonate one of those guys. Those electrons from the bond that is really tiny, but there, go onto there, and these guys go up here, and we get only 2 hydrogens on this guy now, which then can go ahead and go, hey, we made H2O H plus, because we just made hydronium, and this guy can steal that proton, and we get so this is the intermediate, but we get to automerization, right? We are going to do a bunch of stuff with this in this chapter. And we're starting with an aldehyde because when you have a ketone, if we're going to start doing alpha proton chemistry or alpha carbon chemistry, I'm going to call it alpha carbon because I want to say because like from this carbon, you have to go 2 steps technically to get to the hydrogen. I mean, not exact, like it doesn't really, but the hydrogen's attached to the alpha carbon, so I'm pretty sure it's just the carbon that is referred to as alpha. But if we're going to start doing alpha carbon chemistry on ketones, well, there's 2 different spots where we have alpha protons, and if we make this into its enol form, we are going to have 2 possibilities, right? That OH this way, and OH that way, right? There we go. Sort of a little triangle. And you could tell me which of those is more stable, right? Is it the one on this side or this side? That side, right? Because it's more substituted. But, I mean, is this so much more stable? And is this so unstable that we're literally never going to have any of this? No, this whole thing is in equilibrium. That's not so much more stable that we don't ever form this. So, if we start doing chemistry with our alpha carbons here, we've got like multiple products, right? Because whatever we do, we can pick one of them and do our chemistry, and then we have to go back to the beginning and do the exact same thing on the other side. So, in this chapter, chapter, you're going to see a lot of aldehydes because, well, there's only one option. Or we're also going to make use of ketones like that, and mostly that, because it's easier to draw, because once we get 4 things, then we start doing these, and even if we don't really have to draw the wedge and the dash because they're all carbons, still, it just looks funny to draw 3 things coming from there, so. But we're gonna use a lot of these and these in this chapter so that we only have to deal with one side. When you see your problems, pay attention to what's going on both sides of the carbonyl, because we will sometimes, occasionally, look at problems where there's 2 things that can happen, and you have to show me what are the 2 products that we'll get out of this or something. But, yeah, cool. That way I don't just not mention it, and then it seems like, oh yeah, now we have 2 possible products. It didn't seem like we did in lecture. We're going to use a lot of these, so often we're not going to have 2 different things on purpose. So, the majority of the negative charge in this is on the oxygen, on, I guess, the hybrid, the enolate anion. So, enolate anion, the thing in between tautomerization, is the thing that we are going to, yes?
Does it matter which resonance structure we use during the mechanisms? Because in the book it says the one with the negative charge on the oxygen is the more contributed one. But then in all the mechanisms it shows the one, like that one right there, where there's a negative charge on the carbon.
So, in terms of grading, I don't care which one you use. In terms of aesthetics, negative charges look dumb on carbons, as do negative charges along with the lone pair. And because we already don't draw hydrogens, not drawing the lone pair when you draw the negative charge on the carbon, it gets very, like, it's way too crowded to really do this. Like, it looks dumb and I don't like it. And it can make it hard to see what's going on. So aesthetically, I hate this, and I would always prefer that we do, let's see, we'll call this R, we'll do this. We'll do all sorts of R's, and wait, there we go. I would always prefer we do this, and then our, let's see. Okay, yeah. I guess I wanted to draw that with this, but whatever. This guy is our electrophile, right? And this was a carbonyl, so this kind of looked like an electrophile. But if we draw it this way, now we don't have 2 carbonyls, so it looks like we've got 2 electrophiles, which I guess that would be next to a lone pair and a negative charge on a carbon, which is obvious enough that it's, you know, that's the thing we care about. But I would always prefer that we do this. And, you know, reform your double bond when we kick off that. This double bond being technically sort of this carbon / this double bond being our nucleophile. Yeah. So, I'm not going to mark you wrong if you do it that way. I just think that's ugly and crowded. So, enolate anions, yes?
Did you happen with most chapter 19?
You know what? I meant to, and then, like, I remembered that was a thing that I would need to do, and then I wrote a quiz. I went home and took a nap, and then woke up and wrote your quiz, and then wrote the the makeup exam, made both keys, and slept for an hour before I came here. So, good call, thank you. Sorry about that. Create file 19. Pretty loud. 19. Okay, there we go. You know what? Let's just give you guys chapter 20 while I'm at it. We're gonna spend a while on chapter 19, but whatever. Now I can't do it 3 times in a row, only twice in a row. Thank you. Let's see. Okay. So, enolate anions are going to function as nucleophiles. They're going to be able to function as nucleophiles in SN2 reactions and in carbonyl addition reactions. So, I drew this guy out. God, there's so much going on here. That makes this easier to see. I drew out this nucleophilic acyl addition, so, or at least the first mechanism step of that. So we would end up with, we're gonna go up this time because that's what we're gonna do. So I have this double bond as red because that's really the source of the electrons, but I'm also sort of cheating in doing this because we need to know which carbon it actually, like, we're actually attaching stuff to, right? Especially when the electrons come from right in between 2 things. And we know it can't go here because this guy's already getting electrons pushed down there. This doesn't have any extra electrons from the other side. So, we would end up with grab the rest of my colors. We're gonna do the nice pretty bond angle. I'm gonna put these down here. Nice pretty bond angle is gonna be the new bond, which is this guy, between this. So we've got a carbon with and then, of course, we can do things with protons, etc. So we've got that. This looks a whole lot like, this part looks a whole lot like things we've already been doing. So we already know this side. We're learning this side of it. This guy gets to be a nucleophile now. But also, if we throw back all the way to last semester month, for a lot of you can do an SN2 attack. So we don't even have to have this guy. We can have electrophilic, well, like an electrophilic addition. No, nucleophilic substitution. I don't know. I mean, from this guy's perspective, it's electrophilic, right? From, like, we're using an electrophile. From this guy's perspective, we're using a nucleophile. I don't know how you name things like that, but we can take this and attack. So this is kind of like the alpha halogenation that we did like right at the end of chapter 16, where we got a sneak preview of this because we did electrophilic addition. Yeah, addition. And we ended up getting no, substitution, because there was a proton there. We just got rid of the proton because it's acidic. Yeah, and we got a bromine there. This time the bromine's still the leaving group, the negatively charged bromine's still the leaving group, but we don't have to have a positively charged bromine as our electrophile that we're adding. We have carbons on it. And that would reverse the stereochemistry because SN2. So we can do that stuff. And now all of a sudden we're making carbon-carbon, like new carbon-carbon bonds, right? a lot of times previously we've been doing oxygen nucleophiles and nitrogen nucleophiles because, well, our carbon nucleophiles were Grignard and Gilman, and I guess organolithium if you really, really insist. So, like, 3 entire ways to do carbon nucleophiles and like make new carbon-carbon bonds, right? Now, we can just deprotonate the alpha carbon, and it's gotta be next to a carbonyl, but we can make new carbon-carbon bonds and not just attack we can make new carbon-carbon bonds on this guy and not just attack this guy. The carbonyl carbon. These guys are going to react primarily at the carbon. We're going to form new carbon-carbon bonds. We've got counterions like lithium or sodium. We've always got those hanging out around the enolate. It doesn't matter, we don't have to draw them, but like they hang out by this guy because we've got a negative charge around there, and metals like to do that. The metal is going to be more tightly, so this is resonant. I don't have a resonance structure, but it's in resonance with something that looks like this, right? Negative charge is partially here on the carbon, partially on that oxygen. It's mostly on the oxygen, and we can like experimentally see that because metals are going to, like, the metals are over by the oxygen, basically. So that kind of, helps give us proof. Like, they're over there because of that, but at some point somebody didn't know, so that might have helped us figure it out. The counterions are also going to block approaching electrophiles to some degree, so, and reduce the likelihood of a productive collision with the oxygen. So technically, we could take this oxygen and attack something, right? Just as easily, or it feels like just as easily as we could attack this and form a new carbon something bond. We should be able to take this negative oxygen and attack something to form something else, right? And form a new bond right there and have the ether. Part of the reason we don't do that most of the time is because to some extent we've got like sodium or lithium ions just sort of, various salt things hanging around mostly near the oxygen. So the oxygen's just sort of already accounted for. It's just sort of, it's happier over there. But also because, if you make this, and this is all reversible, right? Because, well, this is just a protonate that, and, protonate that and attack this guy. You can do some reversing, right? To some extent, like try and make this a double bond. Not with this guy, because this is a bromine, so that's an SN2 reaction. Those aren't reversible, but if we were attacking a carbonyl, we could have some level of reversibility, right? Because, well, we're either forming a double bond, a CC double bond, or a CO double bond. This guy's more stable, and this isn't like Grignard reaction or Grignard reagent territory where it's just so aggressively nucleophilic that the first thing it bumps into, it is bonded to that for life. Nothing can change that. This is slower chemistry, and it's going to be more thermodynamically controlled. So this bond's pretty stable, but this bond, super stable, super strong, right? We love those bonds, so mostly we're going to get that. Technically, both can happen. Okay, aldol reaction. So, this can be either base or acid catalyzed. And we're going to do the base catalyzed because it has fewer annoying hydrogen transfers, proton transfers, and we'll see if we go over the acid. But, okay, I'll talk about it before I just break this out and start drawing it. Basically, what we're gonna do is one of these carbonyls we're going to, oh good. So basically we're gonna take a carbonyl and we're just gonna use 2 equivalents of it. That way we don't have to fight, we don't have 2 different carbonyls and we don't have to go, well, which one are we gonna call the electrophile and which one the nucleophile? Because like, both of them have alpha protons, so you can deprotonate and do something, so like, I don't know, which one do you do? We just have 2 copies of the same thing, so no worries. One of them just gets to be the nucleophile and get deprotonated the alpha carbon, one of them gets to be the, I guess that's this one, and one of them gets to be the electrophile, like we're used to carbonyls being. So. Okay, we're good. So,